трактор падает, там заряд операции, а потом обратно пройти, а потом обратно вращать.
Thank you very much, and it's my great pleasure to be here and a great pleasure to thank the organizers for this invitation. In fact, I'm a novice in this journal. I published my first paper this year, and it's not the paper I will talk about also. And also I really feel shy talking after the brilliant previous speaker, so let me start from the very beginning that this talk has no relationship to the Saturn rings, and while its subject does get born from the Kolmogorov theory of turbulence, in fact, whether this construction is or is not related to turbulence remains an open question. I think I can say like this. Okay, so let me proceed to rigorous formulations and so we consider a random measure, and let me just for simplicity and for to be more direct, consider the case of just random measure on the torus, just on the circle, in fact. So I have my circle, I have the space of Borel measures on the circle, so finite measures on the circle. And also I have just the I also have just the space of random measures, that is to say... Ой, нет, я тогда должен ходить. Нет, ну лучше как-то, может быть... Нет, подождите, лучше как-то с другой стороны, может быть. Нет, хорошо, я буду прыгать. Ладно, окей. I will jump. So this... It's a conference about chaotic dynamics, and so we shall have a bit of that just in practice. Okay, so just finite Borel measures, and I consider random measure. So this is just a map defined on some standard probability space, just a map from omega to m of t. So this is just my random measure, and the distribution of the random measure is the push forward of the measure p. So this is the distribution of the random measure. So a random measure is just a measure on measures, distribution of the random measure. It's just a measure on measures. Okay, and let me give a key example for the purposes of this talk. It will not be, so this example is due to Mandelbrot, who in fact was starting from the conjecture of Kolmogorov-Obukhov. So just the log normal conjecture in the theory of hydrodynamic turbulence, and then there is work of Mandelbrot, which was continued by Perrier, and the key result was obtained by Jean-Pierre Cahan. Just let me consider the simplest example, in fact, the initial construction considered by Mandelbrot. So I have just binary tree, just usual binary tree. This construction can be realized on the circle. Maybe I'll say a couple words about this in the end, but just it's more simple to draw. So just I have binary tree, and in each vertex of the tree I have, so vertices parameterized by finite binary strings, and to each such finite binary string is assigned a standard Gaussian random variable. So standard Gaussian random variable. And then following Mandelbrot, and Perrier and Cahan, one can consider the following random measure. So it's a measure on the boundary of the tree, which is just the unit interval. In fact, I can consider the following random measure. I consider exponential of gamma is a parameter which plays a key role, of sum of my random variables along the branches of the tree. So then, of course, this expectation can be compute it directly, but let me write it in this form. So I normalize by the expectation of this quantity. And then this is the density of my measure. So I consider this density on the interval corresponding to my binary word, and consider this measure sum over n, sum over omega 1 omega n. So, and this is my measure mn, so dt. This is my measure mn. So, it's a random measure. It's a random measure on the unit interval. So, delta is just the interval of points on the unit interval whose binary expansion starts with these digits. So, on each such binary subdivision of my unit interval, I have a density which is given by this formula. So it is, in fact, a random measure in the sense that to each realization of my collection of Gaussian random variables, I assign a measure on the unit interval. So the beautiful, let me first formulate the beautiful theorem of Jean-Pierre Cahan. This is a theorem that this sequence of random measures converges to M, where M is a new random measure which is called the Gaussian multiplicative chaos. So converges in what sense? And this is what my talk is about. Converges in what sense? So converges in the following sense, that for any interval I in the unit interval, the quantities Mn of I converge to M of I in L2 of my probability space. So this is precise meaning of convergence. And so what is the main result of the talk? The main result of the talk is simple condition, which I will formulate a little bit later, a simple condition that allows to obtain convergence in distribution. So here, please observe that even to write this convergence, I need it to be the case that all my random measures are defined in the same probability space. But in fact, in applications, in particular I'm interested in applications to point processes of random matrix theory. This is a subject that started from work of St. Petersburg physicist Jan Fedorov. In applications one has random measures defined on different probability spaces, and I would like to have simple formalism. This is what I present today. Simple formalism allowing to obtain convergence of such random measures in distribution. When they are defined on different probability spaces, and this will be the main result of the talk, to which I will come in the end. But let me first say how this is related to Kolmogorov theory of turbulence.
Concerns that they are defined on different. Why is it so concerned that they are defined on different probability space? You may consider direct product of all spaces and then they.
Of course, but this does not help me. Of course, this does not help me because still it would not be such type of convergence. Of course, I can. Sure, there are many ways of placing random variables defined on different probability spaces onto the same probability space, and also there is an abstract theorem of Skorokhod which allows to reduce convergence and distribution to pointwise convergence. It's an abstract procedure that works just for any collection of random variables. Maybe it's possible to argue like this, but this is not what I will present today. So maybe, okay, you know, if I was not able to do it, it doesn't mean it's not possible, but this is not what I do.
Another question, what is T in that formula on the right blackboard? dt, what is T?
dt is the dimension of unit interval.
On unit interval?
Yes. So, excuse me, the measures before the limit are absolutely continuous measures on unit interval with piecewise constant densities, with densities which are constant on each dyadic subinterval, but this constant density depends on the randomness, depends on the random round. At the same time, convergence, it's not the densities that converge, in fact they don't, and I will explain right now why not, but it is the measure that converges, and this is the beautiful idea of
The limiting measure has density.
No. The limiting measure, and I will explain it, that's exactly what I'm going to explain. It's very simple, that's exactly what I'm going to explain right now. So, okay, so why this is born from hydrodynamic turbulence? In fact, turbulence, and this already Leonardo made such drawings, turbulence proceeds by a sequence of worlds, of smaller worlds which are, well, I cannot draw like Leonardo, but just, there are worlds and then there are smaller worlds and then there are still smaller and so on, and smaller and smaller and smaller. Okay, so Kolmogorov and Obukhov made a conjecture following criticism of Landau in 1962 that the dissipation of energy is in fact a log normal random variable. And the motivation behind this conjecture, which is written black and white in paper of Yeglom in Baklava, is the following, that Yeglom says following Kolmogorov and Obukhov. We take dissipation of energy average on some cube. Then we subdivide it into smaller cubes. Then we subdivide it still into smaller cubes. And the Kolmogorov self-similarity hypothesis is precisely the statement that the conditional distribution of the dissipation of energy on small cube conditioned on bigger cube does not depend on the size of the cube. So these are independent variables. So the conditional distribution of this conditioned on this, the conditional distribution of this, condition on this, and so on. These are independent variables. It's written, again, black and white in Yeglom, and also in Kolmogorov's 62 paper. And then the sum of independent random variables, everybody knows that this is central limit theorem. So the conjecture of Kolmogorov and Obukhov is that the dissipation of energy satisfies the log normal law. This is again written in 1962 paper of Kolmogorov. Okay, but this is not what Van der Grot, Pereira, and Kahan do, because in fact, if you look at this density, so this is a Gaussian random variable of variance n. The exponential moment is, of course, exponential. I wrote it in this form just to stress that this can be written also in non-Gaussian case, just for this reason. So this is, of course, exponential gamma square n. But of course, almost surely, with overwhelming probability, this quantity has size square root of n. So all these quantities, each of these quantities almost surely tends to 0. So the thing that is in the exponential tends to minus infinity, and the exponential of minus infinity is 0. So each of these quantities tends to 0. On the other hand, for Gaussian distribution of variance n, there is exponentially small probability that it will have size not square root of n, but n, the variance. This probability is exponentially small. But I also have exponentially many dyadic intervals. So if the exponents play out correctly, so that is to say gamma is sufficiently small, then there will be these exponentially improbable splashes on a counter set of positive Hausdorff dimension, zero measure, but positive Hausdorff dimension, and this is precisely the random measure. This is precisely the limiting variable. It's completely different mechanism in comparison with the central limit theorem of the Kolmogorov-Obukhov conjecture. So this is the mechanism, and it also has the advantage that it is a theorem with a proof, as opposed to papers of Kolmogorov and Yeglom, which are written on physical level of rigor. So just this quantity converges to random measure. It's, by the way, reasonably simple. The proof itself can be written on 2 lines. So just this sequence of random measures converges in this precise sense. Okay, so let me now pass to the following characteristic of a random measure. Given a random measure, it's a situation that often arises in applications and arises also in non-Gaussian random measures. Because again, my aim, following problem posed by Fedorov, is just to obtain convergence to such Gaussian multiplicative chaos for measures arising in point process. Let me again say that this is a big subject. Just there is work of Fedorov himself, of Keating, of many authors, of Bourgard, his authors, Lacan, many authors, Najdodel, Likebali, there is Shaibi, there is a big sequence of works. Christian Webb, it's certain that I have not listed everybody. So just, Berestitsky also, just the point is that I'm interested in convergence in distribution of sequence of random measures, possibly non-Gaussian, to this Gaussian limit. Each random measure is defined on its own probability space. Okay, but let me first start with a situation when all the measures are defined on the same probability space. And then it is possible to introduce the following characteristic of random measures, which arises both in Gaussian and in non-Gaussian case. So given two random measures, m, m1, m0 and 1, two random measures on the same probability space, random measures on omega. So, and I can consider, I said that the torus, I can consider any compact metric space Z here. It is more convenient for me to consider compact metric spaces, just even if it's not so very important. Okay, so all random measures on omega p. And just then the correlation function of such a random measure, so given I and j Borel subsets of Z, m0I, m1 of j, in many applications the situation arises that this is just an integral of some function. Some function, so on my space, on my circle there is the Lebesgue measure, so I assume that my space, key example is circle regulated interval, that my space carries a measure, which I fix and denote by ds. Even though the random measures are almost surely singular with respect to this measure, but this is just the key assumption that my measures have such, the measures may coincide, they have such function, which is just the quadratic correlation of my random measures, maybe of the measure with itself. The measure, it is also possible to write it for the same measure, or it's also possible to write it for different measures.
So this is expectation R.
It's possible to write it for different measures.
So this is expectation R. I and J is signals, right?
I generate intervals, yes. I generate intervals, yes. I generate intervals. But it's also true for any Borel sets. So this is positive function. The key example is that when BST is just minus logarithm of S minus T. This is very beautiful. This is very beautiful. Yes, because it comes from here. Because if you look at correlation of Z, so this is the key point. As n goes to infinity, these random sums, obviously their variances tend to infinity, their variance is equal to n. But the correlations do not tend to infinity, because if I have two paths, and this is already in Mandelbrot, just if I have two paths, then at some point they diverge, and starting from this point, the correlation doesn't change, because these developments are independent, so they cancel out the expectation. So the correlation is just the length of this interval, and this is precisely the logarithm of S minus T. This picture is especially beautiful, please allow me a very small digression, it's especially beautiful on Lobachevsky plane. So on Lobachevsky plane, it is possible to consider, and just it is a very classical object, Lévy fields. Lévy fields, so fields, Gaussian fields, where the variance of, so these are fields, for me it's convenient to consider it as cocycles, so Gaussian random variable is assigned to a pair of points, PQ, to a pair of points, and the variance is a distance up to an additive constant. Plus how large or not, plus how small. Or larger or smaller, both in terms of the distance. So it is a distance. The variance of my Gaussian random variable is equal to the distance between the points, and also I have the cosine identity. Okay, so this is very similar situation to this one, and if I have two such random variables starting from the same vertex, then of course the variance goes to infinity because the distance goes to infinity. But the correlation of this quantity is of course the sum of these two distances minus this distance. But this has finite limit in Lomacevsky plane, as opposed to Euclidean plane. Because in fact, this is precisely the Gromov product of this. This is the distance from this point to the inscribed circle in my triangle. But this stays finite. So this stays finite, and this is precisely the limit. Here it's the same, but the triangle is completely degenerate. So it's completely degenerate. The triangle is a tripod. And in fact, just this is so in triangle on the tree, the sum of these distances minus this distance is precisely the common segment of the geodesics, and this is precisely what is written here. Okay, so this is the key example, but for me the key point is that this correlation function exists, and then it is fairly straightforward to prove. How much time do I have? Say it?
13 minutes.
Fantastic. So it is fairly straightforward to prove that just if let me write. I have my sequence of measures and all defined on the same probability space, and I have my correlation functions, just EMN of I. I just copy what was written on the other, or is just the integral B and K. And so, just if the quantities B and K converge to a limiting quantity B as both N and K, so this is now a rigorous proposition, very simple. If B and K converge as both N and K goes to infinity in a one of Z cross Z, Z1 can think just of the circle, the S cross dt, in a dominated way, Then the measures, then Mn of I converge, Mn of I converge to M of I, to some, there exists random measure M, such that Mn of I converge to M of I in O2. So this is a very simple statement. It's just two-line verification. But my point here is that I would like to have such statement also for measures defined on different probability spaces. And in fact, now I consider No, it doesn't matter. No, that's the key point. No. The Gaussian condition completely does not matter. The Gaussian condition completely does not matter.
No, bounded measure is bounded.
Bounded, how do you mean?
No, Gaussian measure is not bounded.
In that sense, no. Excuse me, yes, thank you very much for your question. So, I said this, but, and maybe I even wrote this, but maybe not very clearly. So, the total measure, let me say this again, just Mn of Z is in L2. Is in L2, but I do not say that it is, it's in L2, but I do not say that it is bounded, for example, this probability measure. And in fact, it is possible, and one can look at this formula, it is possible for total measure to be arbitrarily large. It is almost surely finite, but it can be arbitrarily large. So in fact, this quantity, Mn of Z, it has very heavy tails. Because it is exponential, it has tails like it has, yes, very heavy tails. It has, it does not have any exponential moments, it has polynomial tails. It has very heavy tails.
You mean a call of positive measures, right? Call of positive measures.
That's exactly right. That's exactly right. That's quite precise. Okay, so, that's quite precise. Okay, so now I consider the measures defined on different probability spaces. So I consider the sequence of sequence of sequences of measures. I consider measures M, N, let us write it like this, which converges in this sense, which is to some limiting measure M infinity M. And this takes place on probability space omega M Vm. And also I need the following condition, which, by the way, is, for examples like this, which is verified in completely straightforward way, that the measures M and N converges in distribution to some M and infinity. So here convergence is only in distribution. Convergence in distribution. Okay. So my claim is that if this convergence, so this is the main result. So if this convergence maybe also it's possible to turn that. Okay. So if this convergence is uniform in N large, in the sense that, so I said that it is in dominated way. Let me introduce the notation. B plus is just the supreme of P and K. So B plus of ST, and I require that it be in L1. Okay, so just if B plus does not depend on N, does not depend on N, and convergence in L1 in here in star is uniform in M. So P plus does not depend on N, and convergence in star is uniform in M, in L1. Then in fact, then in fact M infinity n converges to M. Converges in distribution to a limiting measure. Then there is convergence in distribution. Then there is convergence in distribution. So if there is convergence, if this convergence is uniform, and there is here just convergence in distribution, then there is in fact an infinity convergence in distribution. And so just the, how do I say, the formalism in, how do I explain this? Usually what one wants is to pass to convergence of these Gaussian measures, provided that I know the convergence of these fields Y's, just for finitely many Y's. So here, let's consider just this case, but in fact in the situation of point process, it's a very similar situation. Imagine I have just some Y's which are maybe not Gaussian or whatever, but they converge to this limiting, so some Y's depending on n, which need not be Gaussian. But they converge to Gaussian limit in the sense of finite dimensional distributions. They converge to Gaussian limit in the sense of finite dimensional distributions. Well, I need a little bit more, in fact, that they converge with convergence of exponential moments. So in short, these quantities for fixed and small, for fixed depths of the tree, they converge to corresponding Gaussian distributions. So this is just a statement about convergence of finite dimensional distributions. Then I claim that if this convergence is uniform in n, then also there is convergence to Gaussian multiplicative chaos. Then these infinite measures also converge to Gaussian multiplicative chaos. And this is just precisely the main result. So if the convergence here is uniform, then in fact there is convergence to Gaussian multiplicative chaos. Okay, so now I only need, so in other words, how does it? So here I have convergence in distribution. So here I have M infinity n, which converges M infinity n, and here convergence is in omega n. So, provided this convergence is uniform, and for these limiting measures, these Gaussians, I already know by theorem of Kahan that they converge to limiting distribution, and they are all defined in the same probability space, and I know that they converge in O2 sense. So the point is that provided this convergence is uniform, I can now close the commutative diagram and say that there is, yes, that here there is convergence in distribution. There is convergence in distribution. And this is the key point of this result. And in fact, let me just say very briefly that this can be said in very general terms. So in fact, let me just say here, just that it is possible to formulate, how do I say, if I have, it is possible to formulate this transition in very general terms, in terms of conservation of uniform continuity for maps in the space of measures. If I have some transformation of Borel probability space, just it's completely general formalism, but transformation which depends on the measure of this space. So I have just some Polish space. For me, this Polish space is space of realizations of process on, let's say, the circle. And I have transformation from the space, but which depends also on measure of this space. So something like this, by the way. Here I have transformation of my random variables, but this transformation of random variables depends on the measure on these, depends on the measure given on my space. Okay, so it is not just, excuse me, it is not just, please observe, this transformation, it's not just transformation which depends on the realization of my stochastic process. It is also depends on the measure here. Okay, and then maybe it is a paper which is published in probability theory and related fields that just one can see. Let me just say that it is possible under some assumptions of compactness to give general conditions when this, so this is probability theory and related fields 25. It is possible to give general conditions when the correspondence that passes from this map to its action on the space of distributions, So then when it is possible to give fairly general condition when this to this is in fact uniformly continuous. And this is quite precisely what is used in proving this convergence of random measures. Thank you very much. Thank you.
Some short questions, not.
Long question, I will ask later.
But maybe we have 1 minute still, right?
No, I expect there is no short answer.
No, I think I have answered to your question.
No, I just wanted to explain is it possible to explain that, to compare your result just in the context of Mandelbrot that example, what is the difference of your result with the original result of convergence which you presented?
Yes, okay, thank you very much. I tried to say this, but I didn't say this very clearly. So, of course, in the original example of Mandelbrot, when all measures are defined on the same probability space, there is no need to say anything more. It's already all there. So, when all measures are defined on the same probability space, this result doesn't give anything new, and it doesn't claim to give anything. So the point is that, for example, in the study of random matrices, in the study of point processes, what arises is probability measures that are random measures that are defined on different spaces. For example, on space of Hermitian matrices, on space of infinite configurations of points on the line, and there is no Gaussian structure directly there. It's not Gaussian, this is the key point. I consider convergence of non-Gaussian random variables to Gaussian limit. And I want to take exponential in this convergence and distribution. Thank you very much for your question. Maybe I didn't say this so clearly enough. So at least I tried to answer.